In this section we're going to be looking at equations of tangent lines to a curve, slopes of tangent lines to a curve, and in general just what is the slope of a curve at a particular point. We'll also be talking about the derivative at a particular point as well. Now when we start to define the derivative, we're going to be deriving it from the difference quotient using the concept of a limit and also the idea of average rate of change. Now again, we're working at a particular point. So let's go ahead and look at a graph that probably looks a little bit familiar. If I wanted to find the equation or the slope of this tangent line to the curve at x naught being the initial value, I know the tangent line skims a graph. So this gives me a pretty good idea of what the tangent line looks at. So here's a tangent line. Now the problem is this. In order to figure out the tangent line, I need to be able to find the slope, and the slope is defined to be the change in y over the change in x, and that goes back to average rate of change. Except to find the change in y over the change in x I need 2 points, but to find the tangent line I'm only working with 1 point. So what we do is we work with the secant line instead. So for instance, I might estimate the slope of the line at this point by saying, you know what, I'm going to use the point x naught, and then I'm also going to use the point x naught plus h. So the distance here between these two values is a distance of h. Now just as we were looking at this, my x value is x naught, my y value is over here at f of x naught, and that means I plug x naught into my original function to see what's going on here. Well, if I plug x naught plus h in, I end up with this point right on the curve, and my y value would be over here at f of x naught plus h. Now this tangent line slope right here can be estimated with the slope of this secant line through here. And if we look at this, it doesn't really do a very good job of this estimation, but what ends up happening is if I take this value of h and I move this point closer and closer over here, what's going to end up happening as h gets smaller and smaller is I'll get a better and better estimate of the equation or the slope of that tangent line. So let's move h over here. Let's move it even closer. So h is much smaller here, and then I can see that the slope of this secant line is very, very close to the slope of the tangent line. So this is a secant line, and over here we also had a secant line, and as my points of my secant line got closer and closer to the point of interest here where I wanted to find my slope of my tangent line, what ended up happening is I got a pretty good estimate of the slope of this tangent line. So what's happening here is I want this value of h to go to 0. I want it to get smaller and smaller and smaller, and so pretty soon those 2 points are so close together that it basically estimates the slope of that tangent line very precisely. So what do we get out of this? So basically, the slope of the curve and we'll just say any general curve y equal f of x at a particular point P, and this point P is defined to be x naught for my x value, and my y value is going to be represented by f of x naught, and that's functional notation for just saying plug in x naught into my function and see what I get back out. And so that slope is the number that will be given by m, and of course m is the value that we use to represent slope. M equals the limit as h goes to 0 of f of x naught plus h minus f of x naught all over h. Now this might not make sense because it looks like it's this really complicated expression, but really what's happening here is this is just the change in y over the change in x. So let's go ahead and look up here. Here's the change in y, f of x naught plus h, that's right here. F of x naught, so it's your upper minus your lower. And this right here, this value of h, is this just the distance between x naught and x naught plus h. So if we wanted to, we could take x naught plus h minus x naught and I'd still get h. Now this is definitely one that you'll want to memorize, but we do need to add a little bit to it first. This is true only, of course, provided the limit exists. If the limit does not exist, then what happens is I usually have no tangent line that's possible, or I have a vertical tangent line. I have one of those two cases, and we'll address those two cases here in a little bit. So the other thing that we can finish up with here then is the tangent line to the curve at the point P. And again, the point P is given right here as x naught, f of x naught, is a line through the point P with this slope. So what basically this means is this will yield a slope. It could be 2/3, it could be -1/2, but this yields a slope. So this we will definitely want to memorize. This is going to be the limit definition of the derivative pretty soon, but right now it's just used to define slope. Now if you do not have Maple open up, you might want to pop it open because we're going to be using it in this next example. Now this next example that we're going to look at is based on a function that we've been working with quite a bit, and it's a function that you should be able to graph. So what I would like you to do is to find the slope of the curve, and the curve that we want to work with here is y equal 1 over x squared at any point. And we're going to say at any point x equal a cannot be equal to 0, because if a was equal to 0, you can see I'd have a problem. I'd have an undefined function. So it's difficult to find the slope of a curve basically where you have a vertical asymptote. So to get started here, let's go ahead and graph this. Now this is a graph of 1 over x squared, and again I encourage you to know these basic graphs. So this is a graph of 1 over x squared. And what I'd like you to be able to do is to find the slope of this function at any particular point. So you can see it could be any of these. Now over here on the left hand side it looks like I have positive slopes. Over here on the right hand side it looks like I have negative slopes. So that'll kind of be interesting to see what we can come up with for an equation. So slope is equal to limit as h approaches 0 of f of x naught plus h minus f of x naught all over h. So this is what you should have memorized. Always right to start. So before you even start a problem, let's go ahead and write down the formula that we're going to be using, and then let's go ahead and populate that equation to try and find our solution. Now for this example, what's going to happen here is we are going to let x naught equal some value of a. So let's go ahead and populate our equation and see what we get. We have the limit as h approaches 0 of f of a plus h minus f of a all over h. Now if I took my limit right now, I would get 0 over 0, which is indeterminate, which means to do more work. Now a couple quick things here. This is a long problem. We're going to be writing the same values over and over again. A couple things I want you to note. Never drop your limit notation. A lot of people have the tendency to just drop notations if they're not going to be using them right away, and then at the end they might forget them. So my rule is do not drop limit notations, and I'll be looking for that in your homework log, so definitely don't do that. So what we want to do then is we want to actually plug in, and I'm also not dropping my slope notation because I want to remember what this actually is. So we have the limit as h approaches 0 of f of a plus h. That means I plug a plus h into my function 1 over x squared. So up here, everywhere I see an x, I'm going to put in an a plus h. Everywhere I see an x, I'll put in an a, and this is all over h. And again, if I took my limit right now, I would get 0 over 0, which is indeterminate. If it's indeterminate, it means to do more work. And the more work that we're going to do is to find a common denominator and try and get rid of these layered fractions. So the first thing we need to do is find a common denominator. Now I want you to look at this pretty carefully. This is a very, very common problem to run into when we're working with these types of questions. So if you get stuck on this and you're not sure what happened, please make sure you hit pause. Please note in your notes, put a big star so we make sure you ask in class when you get a chance what we're doing here. But this is algebra. The rest of this problem is pretty much algebra until we get to the very end. So it looks like between these two, this overall numerator, our common denominator would be a squared times a plus h quantity squared. Well, I'd have to multiply top and bottom by here by a squared, and here I'd have to multiply top and bottom by a plus h quantity squared. Now this h is actually h over 1. When you divide by a fraction, you're multiplying by the reciprocal. The reciprocal of h over 1 is 1 over h. So what this boils down to is I have h a squared a plus h quantity squared when this flips. Now in the numerator, I'm subtracting this entire binomial squared. So to make sure that the negative sign distributes, I FOIL it out. I have a squared plus 2ah plus h squared. Now again, if you don't have the parentheses in place, you're going to have some trouble here. So we have the limit as h approaches 0, and again, do not drop your limit notation. Let's distribute the negative. A squared minus 2ah minus h squared. Now this is the deal. The h in the denominator, not the a plus h, but the h is causing me problems, because when I try and take my limit as h approaches 0, I get a 0 in the denominator. So that's where the trouble is. So it's my great hope whenever I do these problems that everything will cancel in the numerator except the terms including h's. Now that I have all terms including h's here, I can actually factor that h out. And then as soon as these h's cancel, I'm ready to take my limit because I've kind of gotten rid of where the problem was. So I have minus 2a minus h, not plus, but minus h, all over a squared times a plus h quantity squared. And now we're ready to take a limit. Now if we wanted to, we could expand this denominator, but there's really no reason to. It's just a lot of extra work. What I can do is take my limit right now. So h goes to 0, this h goes to 0 as well. So what I'm left with here is the slope is equal to the limit as h approaches 0 of negative 2a all over a squared. And actually, that's incorrect. Remember I said don't drop the limit notation? Well, we should have dropped it, because now I've actually taken the limit. I took the limit as h goes to 0, so now I'm just left with the slope is equal to negative 2a all over a squared, and then a plus 0 quantity squared is just another a squared. So I've taken my limit, I've dropped the limit notation, I can divide the a into either one of these, and I end up with negative 2 over a squared times a, which is a cubed. So this is the slope of the curve, or the slope of the tangent line at any point along the graph. So let's go ahead and clearly define that. The slope of the curve, y equal 1 over x squared at any point x equal a, is given by m equal negative 2 over a cubed. Okay, so if I knew my value of a, I could find the value for my slope. So if we look at this, it's kind of interesting. If I have positive values for a, which means I'd be in the first quadrant, my slope would be negative. If I have negative values of a, which means I'd be in that second quadrant, my slope would be a negative divided by negative, or a positive. So let's go ahead and look at our picture again. Positive values of a, negative slope, negative values of a, positive slope. So just like we thought it would be. So this kind of gives us the general idea of what the slope would be at any point. Let's go ahead and use the same equation, y equal 1 over x squared, and this time, instead of talking about in general, let's try and figure out at what value of a gives me a particular slope. So where does the slope equal negative 1/4? Well, we know the general slope is negative 2 over a cubed, and I want to know where does this equal negative 1/4. Okay, well this is a nice little fraction set equal to each other, so it would look easy to cross multiply and divide here. So if I cross multiply, if I cross multiply, I get a negative 8 equals a negative a cubed. A cubed equals 8. That implies that a equals 2. So at a equals 2, I would get a slope of negative 1/4. Well, what that corresponds to, of course, is x equal 2. So at x equal 2, I would assume that I would have a slope of negative 1/4. Well, let's go ahead and look at our graph again. Again, it's a nice little thing to be able to throw one of these graphs up for y equal 1 over x squared. So at x equal 2, that would mean I was somewhere over in here. So what I'm saying is the slope of the line here is negative 1/4, and that looks reasonable. It certainly is negative there. So I can kind of, instead of finding the slope, I could be given a slope and then asked to kind of work backward to try and figure out where that particular slope occurs. We could also look at finding an equation of a tangent line. So let's go ahead and determine the equation of the tangent line at, let's do x equal 1. So we get some nice values. Now to write the equation of a line, we need two things. We need the point and the slope. So the point here is 1, and then we'd take this 1 and plug it into 1 over x squared, and I would get 1 back out. And then my slope would equal negative 2 over a cubed, would be negative 2 over 1 cubed, which is negative 2. So the point is 1, 1, the slope is negative 2, so I put this in the point-slope form of the equation, and then I can distribute, add the 1 across, negative 2x plus 3. That's the equation of the tangent line at the point 1, 1. So this is the equation of the tangent line at the ordered pair 1, 1. So we're going to grab Maple and we're going to curve sketch this very quick to see if it does look reasonable to be the equation of a tangent line. Okay, so our original graph was y equal 1 over x squared, and if you put in y equal 1 over x squared, first of all, let's see what happens. Let's go to plots. It doesn't look like we get anything that we're actually interested in finding, but again, it's because of that vertical scale. Now I also know that this graph is going to lie strictly in the first and second quadrants because my y values will always be positive because x is always squared. So I can start at 0 for my minimum and not worry about this and go up to, let's say, 50, and I'll get a little bit better look what's happening here. Instead of even going to 50, I think I'll break that down to even 10. And then the horizontal, let's do something like negative 5 to 5. And again, these are up to you guys to customize how you want, but I would encourage you to learn how to do that because it allows you to have a better look at what's going on with your graphs. So here's a graph. Now again, if I didn't want to, you didn't have to put y equal 1 over x squared. You could just put 1 over x squared and it would work identically. Just wanted to show you another way you can input equations. Now what I came up with for here was tangent line, and my tangent line was negative 2x plus 3, so negative 2 times x plus 3. Now if you wanted to, you could put y equal, but it doesn't matter. Let's do right click plots, 2D plot. So there's my tangent line. I'm going to change the color of this line just so I can see the difference between my original function up here in red and my tangent line in black. Now one way that we can combine two graphs or two plots is to click on one and not just click on the box but click on the actual curve and drag it and drop it on the other equation. So I can see pretty clearly from here that this does look like a tangent line. Now if I wanted to, I could manipulate this a little bit more. We could, let's say, go negative 2 to 2, or even let's say 0 to 1, because I'm only interested in that first quadrant. We better go a little further than 1 though. Better go to 2. And it really allows me to zoom in and see what's happening here. Now vertically we could go 0 to 4, it looks like would be reasonable. Again, I encourage you to play with Maple a little bit so you get a good idea of how to do some of these things because it allows you to see what's happening pretty nicely. So I'm going to paste this into our lecture. And let's go ahead and see if we can write a little bit on here and see what's happening. So we see right here at x equal 1, because if you recall, that's what I was looking for here at x equal 1, and it does look like this is the ordered pair 1, 1, that this is my tangent line. So this is my tangent line. This is my curve y equal 1 over x squared, and this is the equation of my tangent line. So the equation of the tangent line, y equal negative 2x plus 3, does look very, very reasonable. Okay, let's go ahead and look at another problem. Okay, actually, since I got all that cleaned up, let's go ahead and look at the actual derivative of a function finally. So we've talked about this idea of slopes of tangent lines, average rates of change approaching or going toward instantaneous rates of change, and all this has to do with the derivative of a function. So the derivative of a function at a particular point x naught, we'll say, has a special way that we denote that, and it's called f prime of x naught. Now this is a tick mark, it's a prime mark, it's not a 1. Okay, it means f prime of x. It means the first derivative of my function f evaluated at x naught. So this means derivative. There's other notations for derivative as well, but this is one that we'll start using at the beginning. There's also the second derivative, which would be f double prime, but we'll worry about those in some later lectures. Now the definition of the derivative at the point x naught is equal to the same thing that we were just working with, basically the slope. The change in y, and the change in y is f of x naught plus h minus f of x naught over the change in x. Now remember what happened with the change in x's though, the difference in the x's was just that value of h. And this of course is only the definition of the derivative at x naught provided the limit exists. If the limit does not exist, then I probably either have no tangent line that's possible or I have a vertical tangent line as possible. So a couple quick things. What info does a derivative provide? Well, the derivative provides a lot of info about different things, but the first things that we look at are the slope of a curve. Okay, now when we talk about a slope of a curve at a particular point, we are talking about the slope of a tangent line, basically. It's another way to say the same thing. And another thing that we use the derivative for as we first are getting started with it is for instantaneous rate of change. Now this is instantaneous rate of change with respect to, so ROC is rate of change, WRT is with respect to x, at x equal x naught. And that notation is a little bit ugly with respect to x at x equal x naught, but we'll get used to that, and pretty soon when we start plugging numbers in there it won't be a huge deal. Okay, let's go ahead and look at a problem where we're actually using this definition of the derivative. And as with the slope, and this is the same equation of the slope, so it's not a big deal, but we need to memorize this as well. Now those of you who know all the shortcut rules already for derivatives, you can use those shortcut rules to check your answers, but you're going to have to find the derivative in this first exam using the limit definition. If you don't use the limit definition, there won't be any credit there, because I want you to see how the limit definition defines the derivative and that you'll be able to use the limit definition to find the derivative. So again, use that shortcut rule if you know it to check your work, but do not only use those shortcut rules. So let's look at a question. What is the rate of change of the volume of a ball? Of course, a ball we'll say is a sphere. Volume equals 4/3 pi r cubed. With respect to WRT, with respect to the radius, when the radius is r equal 2. So what we have here is we have a ball that's not inflated, but it's not like a flat ball. It's just a sphere that doesn't have any air in it. And then let's say we start adding air to it. Now as the radius changes, the volume is changing as well. And what we want to know is what is the rate of change at that exact point r equal to. So what we're looking for here is the instantaneous rate of change. Okay, well, that's my derivative evaluated at 2. So that's the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. And this comes from my difference quotient that we memorized from up here. So that's where this came from, right up here. Okay, so let's go ahead. If we took our limit right now, we'd get 0 over 0, which is indeterminate. Indeterminate means to do more work. So f prime of 2, and again, don't drop this notation. Don't drop your limit notation. F of 2 plus h means everywhere I see my variable, which is an r in this case, pi is just a constant, I plug in 2 plus h. So I have 4/3 pi 2 plus h quantity cubed minus f of 2. That means everywhere I have an r here, I plug in a 2. 4/3 pi 2 cubed all over h. Okay, couple quick things here. This 4/3 pi, I could actually, let's go ahead and pull it out front because it makes my limit a lot easier to work with. So let's pull that 4/3 pi out because it's common to both of these, so I can factor it out. And I'm left with 2 plus h quantity cubed minus 2 cubed is 8 all over h. So again, if I took my limit, I'd get 0 over 0, which is indeterminate. Indeterminate means to do more work. And the more work that we're going to do is to expand. So again, do not drop your notation here on the left that says what you're doing. This is a derivative evaluated at 2, so don't drop that notation. So I get 4/3 pi, limit as h approaches 0. Okay, 2 plus h quantity squared, that means to take the binomial 2 plus h times itself. 2 plus h times 2 plus h times 2 plus h, and then FOIL it out, and then distribute the other binomial and expand it. Well, there's also a shortcut you can memorize to that, or you can grab Maple and have it expand it for you as well. But you get h cubed plus 6h squared plus 12h plus 8. And then at the very end I have a minus 8, and that minus 8 comes from right here. So this minus 8 is this one down here. Now it's my true hope that everything will cancel out or go to 0 here except terms with h. And the reason why I want all of these to have h's, and this should happen every single time you do one of these problems, I can factor out an h, cancel with the denominator, and my problem goes away. So let's see what we're left with. F prime of 2 4/3 pi, don't drop any notations, we have not taken a limit yet. If I did take a limit here, I'd have 0 over 0, which is indeterminate, which means to do more work. Okay, so if I factor an h out, I'd left with h squared plus 6h plus 12. And then from here, I can see that the h's will cancel in the denominator with the one in the numerator. So I'm left with f prime of 2 equals 4/3 pi, limit as h approaches 0 of h squared plus 6h plus 12. Now I'm taking my limit, all the h's go to 0, and what I'm left with here then, f prime of 2 is equal to 4/3 pi times, there's only a 12 here, the limit of a constant is a constant. 3 goes into 12 4 times, so I'm left with 16 pi as my rate of change. So we don't have any units on this problem, but it could be, let's say, inches cubed per second, or feet cubed per minute, or something like that, depending on the original units that we were given. So this allows me to find that rate of change as well. So you need a lot of room to do these types of problems. You need to show all your work, show all your steps, so that way if you have a mistake, it's easy to go through and find. But these are the rules here. You don't drop the left hand side here. Don't drop what you're trying to find. don't drop your limit notation until after you've taken your limit. So those are definitely things I'll be looking for when I'm looking through your lecture logs and your homework logs. But again, the whole point of that is so you get used to that notation and you're using it properly, and not only are you using it properly, but it'll help you get correct solutions because you're not leaving some of the values behind. And sometimes people kind of forget what they're originally doing. For instance, they'll start a problem and it gets so involved that they forget what they were supposed to be getting out of it, like trying to find a derivative. So it's good to include the left-hand side. So we've looked at a lot of examples of tangent lines, and we've talked about slopes of tangent lines, and we've looked at instantaneous rates of change, but we haven't addressed one critical issue. What about vertical tangent lines? Now, vertical tangent lines would be lines that were straight up and down. So if we looked at the change in y over the change in x, basically the change in y would be some number. The change in x would be 0 because there's no change horizontally. So I would get an undefined slope. Now we have to be careful here because a lot of people say a vertical line has no slope. A horizontal line has 0 slope. And so it's important that we don't get no slope and 0 slope confused. So I think it's better just to not say no slope. So undefined slope is what we want to think about for tangent lines. And another question is, do all graphs have tangent lines at every point? What if simply no tangent line exists? Well, let's go ahead and look at two quick cases. Let's look at the first case of vertical tangent lines. So for vertical tangent lines, what ends up happening is when I talk about finding the slope or the derivative, we can think about it as derivative as well now, at a particular point, this equals the limit as h approaches 0 of f of x naught plus h minus f of x naught all over h. What happens here is I either get positive or negative infinity. Now this implies that the limit does not exist, but we need to know why the limit doesn't exist, because we're going to look at another case here in a few seconds that the limit won't exist either, but it won't exist for another reason, and it has a different implication or conclusion that we draw from that. So this is the case here that we have for vertical tangent lines. I get plus or minus infinity. The limit does not exist for this particular case. Now one example that we could look at for this is let's look at y equal x to the 1/5. Now this is an interesting graph. This means the fifth root of x. So we already kind of have a little bit of an idea of what this might look like because we know what the square root graph looks like. But I can take an odd root of a negative number. So this not only encompasses the first quadrant like the square root graph would, but it encompasses the first and the third quadrant. So let's go ahead and grab Maple and have a look at what this would look like if we were to curve sketch it. So let's look at y equal x to the 1/5. Now again, if you wanted to, you could come over here to your expressions palette and it would give you kind of the format of what we should be using here for the fifth root as well. So let's right click plots, and again there's other ways to plot. You could write a plot command, and we can see here that we do have this first quadrant value, and I'm wondering if it's going to show us any other values if we change the horizontal, let's say to -10. And of course we'd have to change our vertical then to include values here, so let's go -2 to +2. And it's actually not going to show us these values down here. I'm not exactly sure why. It might be something I have in my settings, but I know that this graph also occurs over here. So what about the fifth root, let's say, of a +32? The fifth root of +32 is 2. What about the fifth root of a -32? Okay, the fifth root of a -32 is a -2. So I know stuff exists down here. I'm just not sure why it's not showing up right now. I might have changed a setting in something. So let's go ahead and do our copy and paste. And let's have a look at this graph, and we'll curve sketch in the rest of it as well. And again, Maple didn't help us out very much here. But the rest of this graph actually comes in down here and moves out in this other direction. It almost looks like an S. So if I wanted to know the slope at x equals 0, and if I plug a 0 in, I get a 0 back out, so it's defined. What I have here is I have a vertical tangent line. So I'd have a vertical tangent line here, and this is not zero slope, this is undefined slope. So this would show us a graph of where we have undefined slope. Now if we went through and did the difference quotient here, it would kind of be pretty ugly to do this one by hand, because I'd have to multiply by conjugates and I'd have fifth roots running around. It would be pretty ugly. And so I'm glad that Maple kind of helps us out here with this. But it has an undefined slope here, or a vertical tangent line right through the origin. Now let's look at another case. In this other case, let's talk about equations or graphs that simply don't have tangent lines. It's not that it has a horizontal or a vertical tangent line, it has no tangent line at all. So what would happen if I was to determine the slope or the derivative at a particular point using that difference quotient or my shortcut rules eventually? I would get something here that was, let's say, instead of 0 over 0, I would get some number over 0, which is undefined. Now this also means the limit does not exist, but for a different reason. So if I get positive or negative infinity, then that means I have a vertical tangent line here. If I get undefined, that means I simply have no tangent line. So this implies no tangent line at that particular point. Okay, so let's go ahead and have a look here. Well, let's look at y equal x, not to the 1/5, but let's use 2/5 here. Now we can see what the effect is going to be. If I have a negative value and I square it, it becomes positive, so this should pop up into the second quadrant. So let's see if Maple can work with this one. I'm just going to go up to this function that I just put in, and I'm going to put in a 2/5, and it should smart plot all over again. And again, it's missing the left-hand side of this curve. I'll have to figure out why it's doing that. But again, I know it's there because when you work with numbers long enough, you get an idea of some of these characteristics. So it's really important to have an idea of what a graph looks like going in, because computers and software sometimes don't give you a very clear picture. Okay, so I know that this graph actually has a mirror, whoops, that doesn't quite look like a mirror image, has a mirror image over here as well. Now what ends up happening here is I'm interested in finding the slope at x equals 0. So I want the slope of the tangent line here, but this comes to a cusp or a sharp point. And so which tangent line would I use? There's a tangent line here, there's one here, there's another here. So basically what ends up happening is there is no tangent line at all. There's no one single tangent line when a graph comes to a sharp cusp like this. So we've looked at how to find tangent lines of graphs, how to look at instantaneous rates of change using this difference quotient, and we've also looked at how to talk about no tangent lines for a graph when we have these cusps. And we've also talked about how to have a vertical tangent line. When I use the difference quotient, I get limits of either positive or negative infinity.